So let me take the pleasure of introducing Gordon Brebner. So Gordon Brebner, I've had the pleasure of working with Gordon for the past 4 years, 5 years, the entire duration of my PhD. And we've been doing lots of fun things together, but he's here to tell us a bit more about his idea for moving towards an open P4 programmable hardware platform. So Gordon is a fellow at Xilinx Labs, and I think the presentation should be great. So looking forward to it.
Yeah, thanks very much, Steve, for the introduction. And we have indeed done interesting things together over the past few years and continue to do so. So what this is about today is, everyone knows about the kind of open software platform for P4, BMV2, the back end, and a lot of people use that. So this is looking towards having something similar, on the hardware front. And by that, I don't just mean, having a particular hardware chip which can run P4, but you're actually having programmable hardware, so you can do not just P4 but experiments around P4, adding hardware to the P4 pipeline. So that's the agenda, and this is a way we might head towards something like that for the P4 community. So the backdrop for this is something which some people may have heard of, some people won't have heard of. Is called NetFPGA. And this is a project that actually originated at Steve's place, Stanford. And scarily, it was almost 20 years ago when you look at the history. And this is a very brief background. The idea was to do networking using FPGAs with programmable hardware. And it originated in Stanford, both for teaching the CS344 class, which indeed still exists today, and Steve has been teaching it the last couple of years with Nick McEwen, but also for research. And one of the original applications was for the ethane project, which led directly to OpenFlow. So in the original OpenFlow and ethane publications, NetFPGA was one of the implementations used for that. So at that time, the board went through several kind of internal versions at Stanford. I may not have got the exact names right. It's my history translation, but the first one had 8 by 10 megabit per second ports, 2001 to 4. Then the second generation was 4 by 1 gigabit ports. And then it was upsized a little and a bit bigger FPGA and became something called NetFPGA 1G. And it's kind of at that point, round about 2007, a kind of broader community was built around it. I mean, other researchers were using it already. But then that led to a sequence of kind of community boards carrying Xilinx FPGAs. And from the seed of the original Stanford boards, there was NetFPGA 1G for 4 by 1 gigabit per second, where Stanford were still leading the community. Then Cambridge got involved, and the next generation was 10 times faster, 4 by 10 gigabits in 2010 or so. And then a kind of FPGA upgrade. It jumped 2 generations from Vertex 5 to Vertex 7. And that's still in use by many researchers today. It's called NetFPGA Sumi. And I forget the exact reasoning for why it's called Sumi. Someone explained it to me once, but I've forgotten. So that's very much in people's hands at the moment. One of the issues with the NetFPGA community is there's been a lot of work, designing special boards for NetFPGA, and then building some hardware infrastructure on top of that to make it easier for people to use. And often that took a long time. And by the time it was completed, the FPGA was maybe 1 or 2 generations older than it could have been. And so there's a kind of lag time in doing this specialist approach. But having said that, NetFPGA in its history has been extremely successful. There's a world map which has NetFPGA flags all over it, a very large number of research groups, and hundreds, literally, of publications round about NetFPGA. So that's a kind of potted history. And what's going on at the moment is, sort of bring it into the 2020s, so to speak. We've been calling it the NetFPGA 2020 project. And the kind of ideas, if you look at today's, there is an open source community around it at netfpga.org, but it's a standalone community. P4 has come along obviously since NetFPGA, and through the good work of Steve himself, who's here, he actually implemented the P4 to NetFPGA design flow, which I'll speak about a little more detail later, but that kind of enabled NetFPGA to be a P4 target. The actual platform on top of the bare board was limited to a set of reference designs which people could then hack at. And as I said, it's been based on these custom boards which have to be done specially. So the idea for the future is to get more alignment with P4.org, and that's really the nature of this talk, is bringing it into the P4 community in a more integrated way, and looking at what's been going on in P4 and is going on in P4, and trying to make this a kind of hardware infrastructure reference for the P4 communities, the kind of hardware analog of BMV2, if you like. And in order to achieve that, instead of having people producing custom reference designs and hacking them, is to have basic platforms which can be directly used by people who are scared of hardware, or can be extended, and that these have P4 compatible APIs from the software world. And kind of importantly, instead of doing custom boards for this project, there's now available generic boards from people like Xilinx, for example, which can be used to underpin this architecture, and leaving it open that other people could come along with their own boards and sit under this architecture. So the idea is the platform architecture is portable across a range of boards, where in the past typically it's been customized for a particular customized board. So we're trying to kind of make it more customizable in 2 dimensions, if you like. So that's the kind of transition that's happening in NetFPGA. And relating the 2 communities, the idea is P4.org is obviously the home of the P4 language and architectures and the API, to try and make NetFPGA into the kind of standard programmable hardware infrastructure for it. The idea is not that NetFPGA gets subsumed by P4, because a lot of people actually use it without using P4 as well. But making it systematically positioned within P4 rather than having it as an add-on. And the hope is that there's a bigger open source community around it. P4.org is now within ONF, which in turn is within the Linux Foundation. So rather than just having a standalone community. And the idea is the crazy world of FPGAs is where I work, but sometimes it's a bit crazy for me, is to make it less a kind of a hardware specialist project and more of a thing that software and networking people can relate to. Having said that, the hardware aficionados still have a role in building the basic infrastructure, adding custom externs, for example, to extend P4 architectures. So that's the kind of general alignment we're hoping for. And to plug what I mentioned briefly, the P4 to NetFPGA, this name check for Steve here. This has been around actually for almost 3 years. And the idea is, we have a Xilinx P4 compiler. We've had that since the dawn of P4, more or less, and it's been a P4 16 compiler since 2017. The idea is a P4 program is compiled into a hardware block, and then that can be implanted into a standard reference design that comes with NetFPGA SUMI. The original reference design has a fixed block written in Verilog for doing very simple packet forwarding, and basically we take that block out and implant in the P4 generated block. That sounds easy, but Steve will confirm it's a non-trivial exercise to implement it. Since it's been implemented, there's actually been great interest, and just as a measure, I've been kind of releasing Xilinx SDNet licenses to the research community, and we're up to about 100 distinct license sites. I think it's about over 80 unique institutions around the world, and literally around the world. So, and that's very much been catalyzed by P4 to NetFPGA. That's really caused a bump. In fact, when this was released, there was a noticeable increase in NetFPGA SUMI board sales. And this has been used in teaching, for example, at Cambridge and Stanford. I mentioned the Stanford CS344 class have been using this, and sometimes have been used as unwitting guinea pigs, by Steve. He's a cruel instructor, trying our bleeding edge, P4 on NetFPGA experiments. But also Cambridge has been using the same thing this year as well. So these are the first practical steps. This was kind of adding P4 onto NetFPGA. Prior to trying to do something more integrated. We have a chance to respin the whole process at the moment. So looking across at P4.org, something that's very relevant to this is the standard portable architecture models, and P4 has the architecture working group. And most people know about PSA, the portable switch architecture, which has been around for some time. And I think the official specs have been out since early last year. It was launched at one of the P4 workshops. And there's also a subgroup looking at something analogous, the portable NIC architecture, named PNA. And there's actually a panel session at this event, discussing P4 for NICs. As people will know, people usually talk about switches when they're talking about P4, but what a lot of people actually have in their hands in their labs are actually NIC cards rather than switches. So the idea is to try and do something similar for NICs in terms of defining a portable architecture. And that's been going on as a discussion following one of these P4 workshops, in fact, where various people from various directions were interested in this topic. And the idea is, P4 doesn't end up with a plethora of architecture models. One thing, this is one of Steve and my fun projects, has been over the past few years, is a thing called programmable target architecture, where you actually extend P4 to describe architectures. So you can see PSA and PNA as being examples. In theory, using these extensions, you could describe PSA and describe PNA, and then automatically synthesize FPGA implementations. So that's kind of research in progress, but it's a kind of open-ended way of people could create their own pipelines, their own architectures, instead of having to take either the standards from P4.org or from particular vendors. So the architecture is very important, because when we sort of look at NetFPGA implementations of pipelines, the question is, what's in the pipeline and what are the components and how can you extend it with externs and such like. So cutting back to NetFPGA 2020 with that thought, the idea, as I said, is to avoid having a divergent collection of different boards, specialist boards, and divergent reference designs that only work on certain boards, and having one standard kind of adaptable platform design. And we're thinking in terms of one that's natural for NIC-like context and one that's natural for switch-like context. And these are open source hardware designs that are available to everyone. The principal PNA doesn't exist yet, but basically the architectures follow the contents of PSA, which does exist, and the future PNA. There's a P4 programmable data plane, the pipeline at the heart of it, or possibly multiple pipelines, and then P4 runtime for accessing the P4 block, possibly embedded with other standard runtime system, like OpenConfig, for example, for using the platform. And the idea is to minimize in a standard-based platform, things that have to be customized by the user or are very specialized but have open-ended hooks. So people can add what I've called inline and look-aside components. So a P4 extern currently would be a look-aside component from the pipeline. You go to the extern and go back to the pipeline. An inline edition would be where you actually add blocks into the pipeline. And one particular block Steve and I have been looking at in past years is for traffic management. At the moment, that's a black box in PSA, and you get what you get with particular targets. But we've been looking at how you might have a programmable traffic manager, and that's something you'd put in line with the pipeline, for example. So the idea is traditionally, NetFPGA has been associated with the board that you take what you get with it, like NetFPGA 1G, NetFPGA 10G, NetFPGA Sumi, etc. Is the P4, the new NetFPGA 2020 brand is more about this logical platform that's built on top of it, and that works on the hardware, and it's kind of standard hardware as well. So we're trying to kind of make people's lives simpler in terms of hardware design. So kind of seeding this from Xilinx Labs, my group is, there's a couple of kind of base components which we've been working on. It was for our own use originally, and we're making these available to the community. It is two components which are implemented on a variety of boards. It's a parameterized design which can be targeted to different boards. But on one side, there's got a network side packet interface, which is an area people often have difficulty with. The CMAC is 100 gig MAC, and then the green boxes are some adapters we put around it to basically make it easier to use. So people using the standard Xilinx CMAC block often have a lot of trouble getting all the signals right. So basically this tidies it up to make it this dotted box effect. And on the other side, we do something similar in the CPU direction. Is we have a CPU and a Linux driver that can run on x86. And then we tidy up a standard DMA interface between the CPU. The current and latest Xilinx block is called QDMA. And we're kind of adding these green boxes to give that a simpler interface, which is very similar to the one coming out to the network side, and some control interfaces. So these are the two basic building blocks just to make life easier in terms of what comes out. And then the idea is these are used to build both the NIC and the switch variants. So this is something we've been using in our own work, and we've made available to various researchers already. Is in between these, we have what I'm calling the user region, and going from left to right, it has packets coming from the network being streamed into the user region, and also from right to left, packets being streamed from the CPU into the user region, and then packets similarly go out of the user region. And what you can put in here is more or less anything. It can be a P4 pipeline, it can be a P4 pipeline with extra hardware that you've designed, or it could be additional hardware. The idea is at the perimeter of this gray box, it has very simple interfaces, so you can focus on precisely what you want to work with. And you'll see the kind of NIC effect. We have the network on one side and the CPU on the other side. The switch one is a bit more elaborate, and this is very much based on the NetFPGA Sumi reference design. So this is a two-port switch because the initial target is actually for a NIC-like card, which has 200 gig interfaces. And here you'll see around the user region, we have some input multiplexing, which can multiplexes together packets from the two ports and from the CPU side. They then go into the user region as aggregated packet flow. And similarly on the outside, there's an output demultiplexer, which then feeds things back to the line. And NetFPGA fans will recognize, the input multiplexer is what's been known as the input arbiter, and the output demultiplexer is the output queuing block. And the idea is, there's some additional standard functions, these blue boxes, which are supplied, as part of the shell to make life easier for people programming. So that's the two. I won't go into the technical details of this, but that's the basic architecture to put a bit of meat on this. And examples of things that can go into the user region. One is we can now replicate the NetFPGA Sumi reference switch by now at 100 gig rates instead of 10 gig rates. By putting that into the user region, the forwarding decisions. The P4 to NetFPGA workflow can fit into this gray box, so one can put in P4 pipelines and you end up with a PSA cell hardware platform. Another thing which can be done with some quote expert extensions to the shell is instead of just having 1 or 2 100 gig max is to have 4 25 gig max or 8 25 gig max. And then, that's yet another thing Steve has been working on. Yeah, by now Steve does all the work on this project. So, and there, in that example, to emulate the NetFPGA SUMI, slightly speeded up, one can plug 4 25 gig ports through a breakout cable into 100 gig port on the shell. And so basically one can emulate precisely what NetFPGA SUMI has done using this platform in a modular way. And then another extension which I mentioned is adding in some programmable traffic management, which is a kind of research topic various people are interested in. So the idea is the user region is kind of open-ended, but the tedious and the messy kind of hardware aspects that often really hold people up at the interfaces, network and CPU, are kind of abstracted away, if you like. So that's the kind of open agenda. And in terms of what does this run on, I said the idea is to move away from kind of specialist boards to more generic boards. And we've been prototyping on, there was an early Xilinx 2-port NIC board, the VCU 1525. There's also a bitware board, the SOC 250 or the 250 SOC. You can name it either way. And it's interesting because the FPGA also has ARM cores on it, so one can experiment with a couple of ARM cores as well as programmable logic. The kind of mainstream family, and that's really catalyzed this generic approach, is Xilinx is now producing not just development boards for playing with new FPGAs, but actually finished boards intending for the kind of data center market, which are called Alveo. And we're supporting the current family members, the U200, 250, 280 with this platform. There's a lower cost and lower size card called the U50, which is around, and we're about to port the infrastructure to that. And then the idea is that the next generation, which for Xilinx is called Versal. The idea is we have this parameterized platform, we can upward port it to the next generation without having to redo all the infrastructure. So that's the kind of reality check. These boards exist, and the people are using them, and the infrastructure is working on them. So that's well in progress at the moment. So the kind of general status on this is towards the end of last year, some initial versions of the NIC and switch platforms have been completed, and Cambridge has been particularly active on the switch side. The NIC side has mainly come from my own group, and then we kind of had stabilized versions in the last few months. The boards were supporting some standard boards, some legacy boards, and with the P4 focus is just again at the beginning of the year, and this was Steve's work, was updating the P4 NetFPGA tool to target this environment, and that also involved there's a brand new Xilinx P4 compiler. The original one, which I've talked about at these workshops ad nauseum over the last few years, it came out of my Xilinx Labs group, and it's been taken forward by a real engineering group inside Xilinx. So this compiler has far better resource use and latency, for example. So that's been part of the work. And in terms of building the community, we've had a small set of early adopters, since January and running through August this year. I'll show you a list on the next slide. We've been slightly compromised by the COVID-19 situation in the last couple of months, because for most people, they can't get into their labs, and it's harder to kind of do work with this as planned, and even getting boards to people has been slowed down because of people not being in the office. So it's got a bit more slowly than originally anticipated, but we're still managing to make progress. And I know of at least 4 people who've got home labs they've built, which have Alveo cards, and they're doing work with. And the idea is to open it up to the general user community in September. There's a kind of 3-day workshop planned, which is going to be based in Oxford, but probably digital and virtual to a large extent. since we're assuming, in September things are not going to be back to the old normal. And really, this talk is seeding the idea of building a kind of joint community plan with P4.org. I've had some discussions with people on the P4 scene, but how we could, just as BMV2 is kind of well established as part of the P4 scene, is how we could make this a more natural part of P4.org as well. So that's the current status, just to show you the kind of places and people who've got hold of this already. You'll recognize the kind of various organizations and universities and people who are actually using it. And then there's a kind of short list. This is things that people are working on, which, when we launch the community, we're hoping that this will enlarge the offerings from just this basic open shell offering. For example, at Lawrence Berkeley National Labs, one of the things to be open sourced is an array of soft network processors called BX, which is a Berkeley extension, I think is the acronym. And the ultimate aim of that is that will be P4 programmable. So people would have a kind of runtime P4 programmable NPU array, which is implemented on top of this FPGA platform. The current FPGA compiler for P4 generates hardware. So this would also give a route where you can do more quick experiments in software. As I say, Cambridge has very much been leading the kind of NetFPGA switch and moving that on to 100G and using high bandwidth memory for experiments as well. The Open Tester project, which is familiar to a lot of researchers, has also been moved across to this infrastructure. In the next one down, the kind of multi-port NIC is something that I said Steve has been working on in the P4 drop-in. And then, there's the various other people, Jen Rexford is implementing a complete P4-based network at Princeton, and the idea is to have this in some nodes of the network, etc. So that's kind of work in progress. As I say, some of these people have very much been delayed due to the current COVID-19 situation, but I think we're all kind of muddling along and making progress on this. In terms of Xilinx, that's I'm the Xilinx person here. We're very much supportive of this effort, just as we're very supportive of P4. So since the beginning of P4, we've been very enthusiastic about it and turned it into products. In fact, so we're kind of helping seed this community with some donations or subsidized or long-term loans of the kind of latest Alveo cards, and a bit of extra support to the leaders such as Cambridge and Stanford. We're open sourcing these platform designs, so either they contain Xilinx IP that's already freely available, or it's stuff we're open sourcing from Xilinx Labs. We were issuing licenses for the SDNet tool flow to researchers. As I said, there's around about 100 of those out in the wild already. And IP license donations for hardware stuff that people might need to build bigger systems. The basics for the open platform I showed you, everything is free. Xilinx actively participates in this community. And for myself in Xilinx Labs, we have kind of various research collaborations, including with the people on the slide I just showed you. So it's something that we're very much want to support as a community effort. And bringing together the two communities in a more integrated way would be a great goal. So just to round off, this is my last slide. The P4 related goals, it's to associate netfpga.org more closely with P4.org by positioning netfpga as a potential programmable hardware platform for P4 that's the standard. The goal is to move from the hardware then networking users, I call it. That's people who do hardware and then build networking applications on top of them. And there's been a lot of that in the NetFPGA community originally. So we're trying to include the networking, then hardware people, so the people who actually want to think about networking and then how do I get this into hardware. P4 is the focus, but we're not ruling out Verilog like hardware description language, because there's a lot of people still doing interesting networking research, using more conventional hardware design. And as everyone knows, P4 can only express a certain range of functions for packet forwarding. So doing other experiments, it's kind of necessary to use more conventional hardware design. Reduce this historic focus on custom boards first, which was time consuming, then building infrastructure, which was more time consuming, and then community building once you've actually got that. So the idea is by taking out these first two pieces as kind of standard offerings that we can build the community much more quickly. And the idea is people don't get stuck with using FPGAs that are 3 or 4 generations out of date. It's much easier to move on to future generations, for example. So the platform I showed you is based on what Xilinx calls UltraScale Plus, the next generation, which is called Versal. We're already starting to make steps to moving towards that, and it's got a lot of interesting extra capabilities. So the idea is it's easier to keep this community up to date. If people want to get newer boards with newer FPGAs, it's much easier just to migrate work and port work. It's not a complete hardware redesign. So that's the goals, and the main purpose of this talk, at the round table, was to let people know what's going on and see who else is interested. As I say, we've got our little early adopter community of about 15 or 16 going at the moment, but come September, the idea is to have the big bang, and it'd be nice to be aligned with P4 when we do that. So on that note, if anyone's interested, you have my contact details there, so you can get in touch.
Great, thanks, Gordon. That was a great talk, and I suppose I'm a very easy audience for this talk because we're already in agreement about pretty much everything that you already said. But I'd just like to reiterate that I think having an easy to use P4 programmable hardware platform will be amazingly beneficial for the community. And I think, and as you mentioned, NetFPGA and BMV2, they should be complementary to one another. They shouldn't be like either do I use BMV2 or do I use NetFPGA. Ideally, I think the development process for P4 programmers should be you start by writing your program in BMV2, you simulate it with BMV2, you do some experiments with Mininet like we have been doing with P4 tutorials and all the P4 tutorials at the developer days. And then once you have that, then it should ideally be as easy as possible to just run it on the NetFPGA to verify that you can run your P4 program in hardware at line rate and do some more thorough performance evaluations. So they should be complementary and ideally support the same architecture. Yeah.
Yeah, I couldn't agree with you more. I think the whole idea is at the end of it, it's much easier for people to do quick experiments and prototype in the software version with the software simulation. That's about getting the function right rather than performance. Having an easy way in which people can more or less take the same P4 code and then try it out in hardware instead of in software. That's the kind of dream at the end of this is people can automatically get, I don't know, a 10x speed up or whatever, or 100x speed up if we're optimistic. So it's really portability is at the heart of this, and the aim of extracting away most of the hardware detail is exactly to get to that position. I mean, having said that, it's not as easy as I make it sound, because people already realize with PSA that the P is for portable, but most vendors have their own kind of variation of architectures and things, and their extra externs or their kind of knobs and whistles. So I think all of us know that portability of P4 programs can sometimes be, unless it's a really simple one that doesn't use extra bells and whistles, it's non-trivial. But
Well, I do know that the SDNet comes with a software behavioral model. At the moment, it's purely focused on just evaluating that one SDNet block, and not uh, it's not easy to build like a software architecture around it. But if there was a way for the SDNet Xilinx SDNet team to open source that software behavioral model, and somehow make it compatible with BMV2, then I think that would greatly like ease the adoption of like the SDNet platform, so P4 developers can build their software architecture around SDNet, around the SDNet behavioral model, and then ideally that architecture would be also implementable in hardware, and so just as easy as possible for people to go from one to the other. I don't know if there's a plan for the SDNet team to make the software behavioral model open source or somehow allow people to build software architectures around it, but I think that would be great if that was possible.
Yeah, I mean, my research guy answer would be, I don't see many reasons why it couldn't be. I mean, one thing to say is, the Xilinx P4 compiler makes extensive use, of the open source compiler framework. So, we're using that in building a back end. And I don't think I'm giving much away if I say this, but actually the Xilinx backend compiler takes the BMV2 model and then uses that as a way of generating its hardware. It doesn't actually go in at the level above. So the software verification framework you describe is actually building very heavily on the P4 BMV2 software. And one particular thing, for example, is what started at Stanford, not you for once, but someone else at Stanford. The P4 packet gen program is actually used internally, and we're about actually to upstream some extensions to the P4 packet gen, which have been done for the Xilinx work. So I can report that on the packet generator side, we are actually about to give back to the that community, that specialized P4 community.
Yeah, that's fantastic. Yeah, and I think something that a lot of researchers don't realize is that you can do quite a lot of uh, evaluations without even getting like a board. So just having the infrastructure in place to write your P4 programs, simulate it with cycle accurate simulations. You can do your timing analysis, you can do your resource analysis, you can get some basic performance evaluations without even touching like an Alveo board. And so as long as you're an academic person, you can submit a request to Xilinx to have them donate like the Xilinx Bravado tools. So you can do quite a lot without even getting a board, which I think as a researcher is really powerful. And if I was new to this whole framework, that's probably where I would start, is just do cycle accurate simulations, do timing analysis, resource analysis. And then once you're convinced that you can run it on hardware, it's just a matter of clicking a button in Bravado, generating the bit stream, and then making sure that it still works properly on hardware, in which case you can do some more thorough performance evaluations. And I mean, it's obviously very fun to do hardware experiments as well. So
Yeah, I think as a researcher, I couldn't agree more with you. Obviously, as a Xilinx employee, I want to encourage people to buy the product. So I have to be careful what I say. And someone told me this is being videotaped, so I'd better watch what I say this time, since we're not just in real time.
yeah, that's true. Yeah, but and one other thing that I wanted to mention was the initial P4 NetFPGA flow was I thought was very useful. There's a lot of people that are using it, that are still using it. There's going to be another talk that I'm participating in that someone actually used it and built something useful. So I'm excited for that talk. But it was also a very good learning experience for us, because we found the ways in which we can make the platform more usable and easier to use for people. And so the new NetFPGA 2020 that Gordon alluded to in which we've ported the P4 NetFPGA flow to that. The goal is really to make it as easy to use as possible. And I was going to use it to teach CS344, except unfortunately that had to get canceled because of the whole coronavirus pandemic thing. So, but maybe next year I'll be able to use it to teach the class, and things should be, I think, much more smooth and easy to use for people. So I'm excited for that.
Yeah, I think the community was very lucky that Steve did this work before he knew the class had to be cancelled. Otherwise it might have been delayed.
Yeah. Class deadlines are always a good practice. Yeah.
Yeah, one thing I'd actually say about CS344, because I've observed it over the years, and in its previous incarnation, it relied on the student implementing stuff in Verilog and requiring hardware expertise. I've had the privilege of being invited along to help evaluate the projects at the end of the day. And since the switch to P4, my observation is the students have done much more ambitious projects than before, when they were really reliant on each pair having some hardware expert there who could do the Verilog. And that's what I've noticed is the move to P4 has made a dramatic improvement to their productivity and their visions of what they could do.
Yeah. It's been a really fun class to teach. Pretty much all the students are also computer science students as opposed to EE students, so almost none of them have hardware experience. And they've all been able to successfully build an fully functioning internet router, do some interesting projects by just writing P4. So I think there's still work to do to make it as easy to use as possible. And ideally, all of the course material will be available for other people to just fork and teach at their own universities. But it's definitely a good starting point. Looking forward to developing the class some more.
Yeah, I think as part of our integration with P4 effort, the education work group is an aspect, and luckily that's co-chaired by Noah Zilberman at Cambridge, who's the leading person in driving NetFPGA along there at the moment. So I think we can make some connections into the education scene as well for P4.
Mm-hmm. Yeah. Cool. Yeah, I think that covers everything that I wanted to cover. And thank you for the talk. It was fantastic. I enjoyed it a lot.
Thanks for having me in your virtual workshop.